Hello, welcome to Digital Gravity Lab. I am Matthew Isler, and this is my second paper as part of the PhD program in Computational Science and Engineering. We've been tasked to review Carey et al., who surveyed the architectural approaches for improving GPU or general purpose GPUs back in 2019. Where he looked at improving performance, programmability, and heterogeneity in particular, and gave a set of future areas to update. So in this paper, kind of introduce it, look at some of the big things that changed since 2019, and the fact that with the last 5 years, and major updates, we need to relook at all the new architectures. The center of gravity in high performance systems has shifted. They're shifting more to GPU or graphical processing unit centric heterogeneity, where heterogeneity is the systems that have both CPUs and GPUs that work together. So for data parallel phases, this transition yields much superior compute per watt, memory bandwidth. But of course, in that there's an architectural changes that have to happen in the programming and in the architecture itself to be able to shape the software and the systems to work together. And so Carey et al. Provided a durable baseline, 3 main structural bottlenecks: control flow, divergence, memory bandwidth or traffic, and limited exposed parallelism. And he kind of looked at 5 architectural thrusts: irregular workloads, bandwidth, contention, serialization, parallelism, concurrency, and then programmability, and last, that CPU GPU integration to better transfer information between them. And so off of that, the problem statement is basically that we're relative to that survey from 2019, what architectural developments have substantially advanced performance, programmability, and that CPU GPU integration for general purpose GPU computing, and how can those inform architectural lens for my future dissertation, which is using GPU accelerated digital twin workflows, right? So in digital twins, for example, a lot of that physics. So physics would be considered a general purpose GPU usage versus doing the graphics side of it. So some of the research questions is basically looking at those irregulars, that bandwidth contention, concurrency, programmability, integration, those fabrics that bond everything together, and what kind of things cross-cut in that. So motivated by those research questions, this paper that I wrote revisits the Carey et al. Taxonomy and with concise synthesis of each of those axes, and it surveys the post-2019 advances that have materially affected those axes, those areas, and looked at it from an architectural lens, those coherent fabrics, task-based runtimes, anywhere designs, the way in which everything is connected together, and I tried to connect it to an evaluation plan in Omniverse, Isaac Sim, for that dissertation projects for centrifugal visual physics platform for robotics. And so the goal is to provide an updated architectural map and that research vehicle, or utilizing that plan as a research vehicle and a test bed to better optimize the program systems I'm using for the fact that it's GPU-centric high performance computing, and most likely incorporate some form of AI systems while the whole dissertation is supposed to remain actionable for reproducible experimentation for others. So in methods, I did use an LLM assisted retrieval and manual screening for pulling literature. I didn't do a exhaustive review due to time constraints, but looked at ACM, Digital Library, IEEE Explorer, and choose a few preprints as well. And I based those polls on the CARE 2019 survey, and those accompanying citations, tried to look forward from those, and then focused on those key areas, which we'll get to what those are in a second. I did prioritize articles and peer-reviewed articles from 2023 to 2025. Obviously looked at whether it's methodologically clear and whether it had relevance to the deltas, which we requested to look at part of this assignment. And I did use a little bit of official specifications related to hardware, time of writing. I didn't include very many of like the Hopper, Blackwell architectures, as note more of the general ideas of how to connect them together and the integrated part. Probably should have added a little bit more of the nomenclature for the new systems, for the overall architectures for the chips, but that I guess will be future work. So looking at Carey et al.'s work, the 5 axes, there's the persistent bottlenecks that control flow, divergent memory bandwidth traffic, limit exposed parallelism, and there's various organized remedies across performance, programmability, and CPU GPU integration. So their framing, Carey et al. Framing was anchored in a SIMT, or single instruction multiple thread core, and work block schedulers and then private shared memories across that, on package caches, and discrete CPU hosts over PCIe. So they have a typical GPU architecture and CPU GPU contrast in their table. So that's linked here as well to their paper. And so since then, there's kind of 5 deltas that dominate the practice. There's execution model flexibility, the out of order like scheduling. There's now it's between that single instruction multiple thread and multiple instruction multiple data analysis, and that placement order has become very important under the new NVLinks and NV switches from NVIDIA. So those are NVIDIA's high bandwidth GPU interconnects and switch fabrics, whose non-uniform topologies make kernel data placement across the islands a very important or first order performance decision. There's the memory fabrics and pooling, the CXL Compute Express Link, which is a cache coherent fabric that attaches pooled memory ties or tiers into CPU GPUs, which extend capacity at higher latency and shift allocator mapping policies into runtimes, and the quality of service capacity issues are improved. Programming semantics have been solidified via the formal PTX model and its extensions. PTX is parallel thread execution, so NVIDIA has been developing a virtual ISA and memory module, which is now more formally specified and extended, and enables safer compiler runtime transformations. And then there's improved graph or task-based orchestration, which has really become a large contrast between the application intent and those heterogeneous nodes. So there's the programming just becomes a lot more straightforward. so there is how that kind of maps. The 2019 survey carries by Carey explicitly scoped 5 threads, as mentioned, and those threads in their table 9 capture the breadth of some of the programming proposals, and we just keep that a little bit intact, but we elevate a bit of system placement, the fabric attached memory, and graph level orchestration. So for single structure, multiple thread core and warp block scheduling, Carey et al. Emphasize divergent handling and warp block scheduling as primary levers for throughput. In Carey's figure 3, depict a monolithic single instruction multiple thread core fed by host over PCIe. And today's execution is often a graph scheduled device-driven pipeline in which that large copy compute are fused a bit more, and while the micro scheduler is important, the dominant wins there come from cross-kernel orchestration and minimizing host involvement in those. Memory cache hierarchy, Carey et al. Emphasize the bandwidth pressure and that the cache scrap pad co-design. You can do section 4, and their high bandwidth memory was already started to improve per package bandwidth and capacity, but that memory is now more of a system problem, where you can use a lot more remote high bandwidth memory over that NVLink and NV switch, which increases coherent CPU, GPU memory via another NVLink, the C2C, and their fabric attached tiers, those compute express links. And new capacity deployments, that the software stack has to actually treat those explicitly. So there's still programming efforts there, but it's being handled a lot more by the coding set. So for emerging pooled memory, the memory says 24 measurements across the CXL switches show visible topology effects that should be feeding into mapping policies. Carey et al. Cataloged cache and DRAM schedulers, but in 2025, these cache DRAM are nested inside the heterogeneous, sometimes coherent fabric, and so the question shifts a bit from coalescence, prefetch more to what lives in that high bandwidth memory, DRAM, CXL, and where are the edges, where the edges of the storage, it takes a little bit longer to process back and forth, making sure that things are stored and pulled closer first versus those edges within the hardware. In data movement and interconnect, Carey et al. Already flagged those interconnect limits, with primary challenge non-uniform fabric geometry. But the NVLink switch has been building the high bisection GPU fabrics. There's still some placement asymmetries, but the GH200 creates a coherent GPU CPU island, and then the compute express links induce shared coherent memory pools which span across the CPUs and accelerators as well. So you can get a much larger memory pool that is still high speed, but there's still a effort there to minimize motion across the latency tiers, and so they're trying to bias or stress in the programming to keep that track back and forth to those fast island segments within the course. and programming memory, security. There's a number of the PTX memory model has been formally specified that I'd already mentioned, and there's a lot more CUDA graphs and things like that are in improving programming. And then more recently, there's isolation and security systems which have advanced, where there's multi-instance GPUs and MIGs, or MIGs, right? Multi-instance GPU. Hardware, which is a hardware positioning that slices a GPU into isolated instances for predictable multi-tenant sharing and quality of service. And so that's kind of started the GPU differential computing on an H100 adds memory encryption and attestation for protected execution. So those are potentially directly relevant to privacy-sensitive digital twins and shared clusters, where we can keep information more secure and isolate particular aspects within the digital twin. The heterogeneity and portability, the carrier's cells call for stronger CPU GPU integration, has been showing up in coherent superchips. The Grace Hopper via the NVLinks, the rack scale NVLink fabrics. If you've seen Jensen from NVIDIA at the NVIDIA events and keynotes, those talk about it every time. They're amazing. If you haven't seen any of those keynotes by the CEO of the world's largest company, highly recommend that. So takeaways for those sections, though, and their different sections. Carriers 5 axes remain still kind of remain backbone. I do kind of think the center of gravity shifted a little bit, where the performance wins are depending more on graph level execution, the tier-aware placement, and the fabric-aware collective, so it knows how to move data information around and where it should be processed a bit better. And the semantics are formalized enough where the compilers and runtimes are a bit bolder and manage more. And the thought with that programming and things not being too deep, I guess, is part of what's motivated me to be able to look a bit more at using the NVIDIA Omniverse project, which are for my dissertation, and using that as a research vehicle, because I'm going to be able to dive in how that is managed. So the architectural vehicle, in my first video, I kind of outlined a adoption plan for it, and where it uses the OpenUSD as the kind of that data layer within the Omniverse, and IsaacSim as the robotics physics layer. And in that, as I build the graphs, that vehicle and the exposed graphs are going to allow me to be able to more succinctly modify what the system does, and to be able to look at each one of these different points, where the OpenUSD clean separates the semantic state from execution mapping. The OmniGraph binds those states to executable nodes with type ports, and that PhysX within IsaacSim does directly provide on GPU processing for all the physics. So it's already a general purpose GPU platform, and but I'm going to be looking at designing this to be more fabric aware, have more task orchestrated physics, have layers to it, and layers to be able to make it more autonomous in that coding. And we'll see what that actually looks like, especially managing energy and things like that for different systems. the points here for each one of the direct research question answers. That yes, there are points in each, things that are directly increasing those irregulars, bandwidth, concurrency, programmability, integration fabric, and there's a number of cross-cutting sets as well. And so that's the core of the paper. I used L, baseline taxonomy. The 5 architectural axes they highlighted are important and have materially advanced in 2019. And it's increasingly interoperable. There are a few open problems: rack scale, concurrency, semantics, predictive placement, portability with a peak, and fairness with that isolation. And there's some obviously limitations to my work, and then I'm very focused on NVIDIA in particular, because the NVIDIA Omniverse is set up to work best with that. And so I'll be looking at quantifying portable performance within that, probe omnigraph scheduling, exercise resilience, co-report time and energy, etc. within that. And we'll keep you posted. Thank you very much for watching. Look forward to your comments. And I'm Matthew Isler with Digital Gravity Lab. Thank you.